Good morning, class. Today we're going to be talking about surface area of pyramids, and we're going to strictly focus on pyramids today, although you are going to see cones start to come up in the discussion. We're actually going to be focusing on cones and cylinders next week, so we'll come back to those. Just to give you a little background on our scenario and why dealing with surface area of pyramids might become important in a company, in a manufacturing company, for example, I'll read you this little excerpt. You can kind of follow along. It kind of gives a little background to our situation here. The way a product is packaged is an important marketing element for manufacturers, and in today's world, it is an important environmental concern for many consumers. Lewis is leading a committee to change some of the current packaging materials used by his company that have been deemed non-recyclable to more environmentally friendly materials. Many of the environmentally friendly materials, however, do not have the same strength or durability as the packaging materials currently in use. The committee realizes that if the materials are changed, then the shape of the actual package will likely have to change to ensure strength and durability. The committee consists of representatives from the marketing department and the advertising department, a product engineer, and a packaging engineer. To begin, the marketing representative provides the committee with feedback that consumers are attracted to packages or to products that are packaged in pyramid or cone-shaped containers. Surface area is a critical concern for the advertising representative as it dictates how much space is available for print. Before the committee goes any further, the advertiser wants to determine the surface area of a cone and a pyramid. Now keep in mind, today we are really only going to be focusing on the pyramid, so we're going to be looking at finding surface area of objects similar to this. Now, there's a couple of specific types of pyramids that I want to make sure that we talk about. One of these is the tetrahedron. The tetrahedron is a type of pyramid that has an equilateral triangle for a base, and then all of the lateral sides are also equilateral triangles. So if you really think about this tetrahedron, we could say that this tetrahedron is made up of 4 equilateral triangles. And that kind of gives us one method of how we could go about finding the surface area of this tetrahedron. Now, suppose that I tell you that the length, the edge of the container is 8 feet. So that means this edge, we could call this 8 feet. Now, since it's equilateral, it means that all of the edges are 8 feet. So this edge is also 8 feet, this edge is also 8 feet, and all of these edges that are shown in the back and down here at the bottom, everything is going to be 8 feet. We're going to start by method 1. We'll start by finding the area of each of the faces. Now, since each of the faces is an equilateral triangle, okay, and I'm just going to look at this face here down at the bottom. Since each of the faces is an equilateral triangle, we can come back to our formula from our previous unit for finding the area of an equilateral triangle. The formula is side squared, square root 3 divided by 4. Now, each of our sides is 8, so 8 squared, square root 3 divided by 4. When I simplify 8 squared divided by 4, 8 squared is 64, and 64 divided by 4 is 16. So that means that the area of each one of the triangles is 16 square root 3 feet squared. Now, if I want to know the total surface area, and we already know that there are 4 triangles, and each triangle is exactly the same in a tetrahedron, all we need to do is 4 times 16 root 3 to give us 64 root 3 square feet for the total surface area. Now, finding that total surface area of a tetrahedron can be pretty quick. Since all 4 triangles are going to be exactly the same, you really only need to find the area of one triangle. But that also leads us to the idea of coming up with maybe a formula that we could use for a tetrahedron. So if we think about writing a formula that would allow us to, and I'm going to highlight this, would allow us to find the area of an equilateral triangle. So we're going to use the formula for the area of equilateral triangle to find the total surface area of one of these tetrahedrons. Now keep in mind that we know that to find the total surface area, we're going to have to find the area of 4 separate triangles. Since each triangle is equilateral, we can use the formula that says side squared times square root 3 divided by 4 to find the area of each triangle. And then we're going to be multiplying that by 4 since there's 4 triangles. Now with just a couple of little quick reducing steps, if I divide by 4 and multiply by 4, those undo each other. And that leaves me with a pretty basic formula of side squared square root 3. So if I wanted to find and I'm going to make a note of this off to the side, if I wanted to find the surface area of a tetrahedron, and keep in mind what a tetrahedron is, it is that 3-dimensional pyramid made of 4 equilateral triangles, I can use my basic formula of side squared square root 3. Using that formula, let's see about another way that we could kind of apply that formula. The packaging engineer provides 27.75 square yard sample of environmentally friendly material to create a model of this tetrahedron shaped container. We want to find the dimensions of the pyramid. So we are almost working backwards here. I didn't tell you anything about the pyramid. I actually gave you some information about the area of that pyramid. So if we think back to the formula, the surface area of a tetrahedron is simply side squared square root 3. This is the formula that we just came up with over here. And the one piece of information I've given you is that the actual surface area is 27.75 square yards. If I plug that into the formula, here's the rest of my formula. This should allow me to actually solve for one of the sides, and that would be the dimension of the pyramid, since we know that all those sides, all those edges are going to be the same. To solve this equation, we will start by dividing both sides by square root 3. So if in our calculator we do 27.75 and divide by square root 3, we're going to get approximately 16.02. Now, what I'm doing is leaving it in the calculator because my second step is to now take the square root of that value. If I take the square root of that 16.02, I'm going to get about 4.00 for one side. So when it asks about the dimensions of the pyramid, we only need to give one dimension since technically all of the edges are the same. So we can see that this tetrahedron has a side edge of 4.00 yards. So it's another way to use our formula, but I do want to remind everybody, kind of reiterate, this formula that we've just used here and come up with is specifically for tetrahedrons, and it is for the full surface area, and that would be the area of all 4 of the surfaces. Okay, now there's a lot of different types of pyramids. So a second pyramid I wanted to talk about here is the square pyramid. Remember that we name polyhedrons according to the shape of their base. So the fact that I'm calling this a square pyramid tells me that the base of this pyramid is in fact a square. It tells us that each side of this square base is 12. So if I come down here and label the side of the base is 12, and keep in mind that's going to be 12 on all of the sides of the base. It then says that the length of each lateral edge is 10 feet. Now there's a lot of information in this picture here, and that's one of the things that we need to talk about, the vocabulary associated with pyramids. When we talk about a pyramid, there's several different pieces of vocabulary we're going to refer to. Sometimes we talk about the base edge. And as it sounds, that is literally the edge of anything along the bases. Sometimes we talk about the lateral edge. The lateral edge, as we talked about in this example, is any edge of one of those lateral triangles. So for example, my lateral edge would be maybe this edge coming down here, this edge coming down here, this edge over here, this edge over here. So actually there are 4 lateral edges, and we know that the lateral edge here is 10 feet. Another thing that we talk about with pyramids is the height of the pyramid. Okay, the height of the pyramid is the height that's going to go from that top vertex point directly down and then perpendicular to the base. The height is often drawn inside the pyramid, but it does not have to be. Okay, and then finally, the last thing that we're going to be talking about, and we'll mention it down here a little bit in a moment, is what we refer to as the slant height. And the slant height refers to the height of one of these triangular sides, one of these lateral faces. So you almost have to think of it as literally the height, but at a slant. Okay, it's important to note though that the slant height is different than the height, and that's going to become a distinction that we have to pay really close attention to. So now that we've kind of labeled a few parts of this square pyramid, let's go back and try to look at finding areas and some surface area and some lateral area. So we're going to start out by some basic things that we can do right away. It says find the perimeter and area of just the base. Well, remember the base is a square, and that square had a length of 12 feet. So the perimeter of that square, since there's 4 sides and each is 12 feet, that perimeter is going to be basically 48 feet. The area of that square is just the one side times the other side. So the area of that square is 144 feet squared. Okay? Then it says that we need to determine the height of the triangular face. Now remember that along the sides of this pyramid, there are 4 triangles that meet up at that vertex point at the top. We want to find the height of one of the triangles, not the height of the pyramid itself. What this is actually asking us to find here is what I mentioned before, what we call the slant height. So I want you guys to picture, and I'm going to change the color here. Let's do a green here. I want you to picture one of these triangles along the side here. Okay, we need to figure out what the height is of that triangle. So I'm going to redraw that triangle so that we can look at it a little bit closer and maybe slide it off to the side here. If we redraw that triangle, the first thing I notice is that, come back over here, the first thing you want to notice is that the base along the bottom is 12 feet. That we already knew. We also knew that the lateral edge here was 10 feet. So this right here is 10 feet. And what I'm asking you to find is that height of that face. And this over here is what we are looking for, and we call this the slant height. So the question is, how do we find that height? Well, keep in mind, since that height is perpendicular to the base, first thing I would probably do is divide this base so that each of these edges is 6. Then we can look at this one right triangle. It has one side of 6, one side of 10, and we're looking for this slant height here. Actually, I'm not going to call it H at the moment. I'm just going to call it B for the Pythagorean theorem. And if we plug in here to the Pythagorean theorem, 6 squared plus B squared equals 10 squared. This is 36. This is 100. So B squared will be 64. And when I take the square root, B is 8. So at this point, what I have found is that the height of this lateral triangle is 8. If you come back over to our main picture, that tells us that this slant height is 8. Okay, so how did we determine the height of that triangular face? We used that Pythagorean theorem to be able to help us find that. Now, as I've mentioned a couple times, this is what we call the slant height. And we can use that slant height to actually calculate the area of one of the triangular faces. Okay, if you look back at the triangle that I drew off to the side here, what I need to do now is find the area of that triangle. And we know that area of a triangle is 1/2 base times height. And we know that the base of this triangle was that 12 feet. Remember, the base is going to be the entire bottom there. And the height of this triangle was 8. Okay, I'm going to go back and highlight those. So we were looking at the base of 12 and the height of 8. That should give us the area of one triangle. When I multiply this together, 1/2 of 12 is 6. 6 times 8 is 48. So one triangle is going to be 48 feet squared. Okay? Now, find the lateral area of the pyramid. Remember that in our previous units, we talked about the difference between lateral area and surface area. Lateral area just refers to let's say, the lateral faces. So in other words, lateral area will exclude the base. In this pyramid, the lateral area is made up of 4 triangles. All 4 of these triangles will be equal since the base was a square. And we've just found out that the area of one triangle is 48 square feet. So if I want to know the lateral area, I need to do 4 times 48. And 4 times 48 is 192 feet squared. So we've got a lot of information at this point. Okay, just to kind of go back for just a moment, some of the key things that we know about this pyramid. We know that the area of the base is 144 square feet. Remember, the base was the square. We know that the area of one triangle was 48 feet squared. We know that the lateral area, keep in mind the lateral area is all 4 triangles, that was 192 feet squared. So with all of this information, we're kind of left with what is the total surface area. We're going to come back to that here in just a moment. But the total surface area of the pyramid would be the lateral area plus the base. So if I go back to the things that I already know, the lateral area was 192. One base was 144. So my surface area would be 192 plus 144. And that is 336 square feet. So there's a couple of steps involved with these pyramids since we do have to find some of the missing information. Now, just like we did with the tetrahedron, we might be able to come up with a formula that could help in some cases to simplify the process. So I want to talk a little bit about that formula and where that formula comes from. We're going to let this, do notice the variable here. We're using a cursive L to represent the slant height of the pyramid. We don't want to use H for height because we don't want you to confuse it with the height of the actual pyramid. Remember that height and slant height are different. So we want to write a formula that allows us to find the lateral area of a right pyramid in terms of that slant height and in terms of the perimeter of the base. Okay, now that's a lot, but let's kind of back up and think about what you guys did there. Okay, the first thing I had you do to find your lateral area, we said that we would take the 4 triangles and we would find the area of each triangle. So we basically did 4 times the area of each triangle. Now, for the area of each triangle, we had to do 1/2 base times height, because that's how we find the area of the triangle. But when we looked back at the figure, the base of our the base of our triangle, think about how that base related to perimeter, because it does say we do want to use perimeter, right? When the perimeter was a square, like in this case, wouldn't this one edge, this one base, simply be the perimeter divided by 4? Remember that to find the perimeter, we would have to add up all 4 of these. So if we knew the perimeter and we divided it by 4, that would give us the side of the square. So if I come back to this formula over here, instead of saying that we did 1/2 times the base, instead of saying base, I'm going to say perimeter divided by 4, because that's really what the base of the triangle was. Okay, now the height of my triangle was actually what we called the slant height. So instead of calling it H for height, I'm going to use that cursive L for slant height. So at this point, our formula says this. We started out with saying that there were 4 triangles. Then we had to multiply 1/2. The base is perimeter over 4, and the height was our slant height. Now, if we simplify a little bit, remember that if I am dividing by 4 and multiplying by 4, those can undo each other, which means I could simplify this formula by simply saying 1/2 the perimeter times the slant height. This is a formula that we can use for the lateral area of any right pyramid. Okay, now you'll notice that you might be concerned with the fact that this particular pyramid had a base that was a square. So we started out with 4 triangles, and we did the perimeter divided by 4, since there were 4 sides to the base. Well, even if I changed that to a hexagon, then there would be 6 triangles, and we would do the perimeter divided by 6. Or if it was an octagon, there would be 8 triangles, and we would do perimeter divided by 8. So no matter what, these values, this one and this one, are always going to undo each other, which leaves us with this formula every time, okay, regardless of what type of right pyramid it actually is. So now we've got this formula. For the lateral area of a right pyramid, we can do 1/2 times the perimeter times the slant height. Now, that means we do need to know the perimeter and we do need to know the slant height, so we still might have to do some work to find those. If I wanted to find the total surface area of a pyramid, as we kind of did up above, the total surface area would just be taking that lateral area and then adding the area of one base. Now keep in mind, when I put this B here, remember that's the area of the base that you're going to have to find. Okay? Write a formula for calculating the total surface area of a right pyramid in terms of the lateral area and the base. Oops, sorry. That's what we did right here. Up above, we had to actually calculate the total surface area, and we've actually already done that right up here when we found that surface area to be 336. Okay, so now that we've come up with quite a few formulas, what I want to do is make sure we understand how we can use those formulas in a couple of different ways. And then I do want to summarize and show you another example of maybe a more complicated pyramid and how we might have to find surface area. Okay, so using the formulas that we came up with a little bit ago, I want you to find the lateral area and the total surface area for a regular tetrahedron whose edge is 8 feet. Okay, well, what did we come up with for the lateral area? We said to find the lateral area, we would have to do 1/2 the perimeter times the slant height. For the total surface area, we said take your lateral area and add one more base to that. Okay, so this is a tetrahedron. Now, again, you really have to remember that a tetrahedron is simply made of its base is an equilateral triangle. Okay, so if we think about this tetrahedron, we know that the base is an equilateral triangle, and we know that the edge of that triangle is 8 feet. We know that these are all going to come up to a point, and that all of these are going to be 8 feet. So if we want to use this formula, the first thing we have to do is figure out what is the perimeter of the base. Well, the perimeter of the base is going to be 8 feet times 3, since it's a triangle, and we're going to be multiplying that by 1/2. The next thing we need to know is the slant height. That one's going to be a little bit harder to find, because remember, the slant height is going to be the height from the vertex coming down the side of the triangle to the edge of the triangle. It is not the height that is going to the middle of the base. Okay, so what we need to figure out is this slant height. Because it's a tetrahedron, we know that all of the edges are 8 feet. So this edge is 8, this edge is 8. So if you think about this one triangle in the front, this is 8, this is 8, this is 8, and I am trying to find this height right here. If I divide my base into halves, make this 4 and 4, I should be able to find the height of this. Now keep in mind, if this is an equilateral triangle, then that means that this angle was 60. This angle at the top was 60, but it got cut in half and is now 30. So we can actually use our 30, 60, 90 triangle to find our height. And using that 30, 60, 90 triangle, the height here would be 4 square root 3. So once I know my slant height, 4 square root 3, I can plug all this back into my formula for my lateral area. And let's see, this is 1/2 times 24 times 4 root 3. Half of 24 is 12. And 12 times 4 root 3 is 48 root 3. That would be my lateral area, and that is in feet squared. Now for my surface area, I'll take that same lateral area, so 48 feet squared, and now I have to add the area of one base. So think back to how we would find the area of an equilateral triangle. Since this is an equilateral triangle, we can do side squared square root 3 divided by 4 to find the area of the equilateral triangle. The side is 8, so 8 squared square root 3 divided by 4. And 8 squared is 64, and 64 divided by 4 is 16. So my one base is 16 square root 3. When I add my lateral area of 48 square root 3, I get a total surface area of 64 square root 3 feet squared. Now, if this problem looks familiar to you at all, it's because we already solved this problem at the start of the lesson. And I want to point out that at the start of the lesson, you didn't have any formulas. At the start of the lesson, we simply found the area of each of the different surfaces and we added them together. Now we've applied these formulas, and I'm going to go back up to the first problem that we did right here. Oops, I apologize. I didn't mean to do that. Okay, I mean to do this. Notice that this was the same problem. The edge was 8 feet, it was a tetrahedron, and look at our surface area. It's exactly the same. And what this brings out, guys, the point is that you do have choices when you're finding surface area. Some people prefer to use what I call method 1, which is just find the area of all the surfaces and add them all together. So if we slide down here, I'm going to come back to that one, okay? Method 1 is find the area of the one base. Remember, in a pyramid, there will only be one base. And find the area of all of those lateral triangles, and then simply add them all together. The nice thing about this method is that you do not have to memorize different formulas. You don't have to know which formula to use when. So some people like that better. Method 2 is using some of those formulas that we just came up with. Now keep in mind that the formulas, though, only work for certain pyramids, so you have to be careful with what formula you're using. For example, if it is a tetrahedron, this is a pyramid whose base is an equilateral triangle, then we can use this formula for finding surface area. If the pyramid is a different type of right pyramid, then we can use this formula for lateral area. We're still going to have to know how to find the slant heights. That's not always given. And we can use this formula for finding surface area. So we can do a variety of different things, and I do like to remind you it is your choice. But I want to show you one more example, and on this next example, I'm kind of going to go back to the method 1 here, where we are, we're just simply going to find the area of all the different surfaces and add them together. Okay, this is a regular hexagonal pyramid. And what that means is that the base is a regular hexagon. Okay, so if I wanted to find the total surface area of this regular pyramid, remember that surface area is basically adding up all of the areas of all of the surfaces. And in this pyramid, there's going to be one hexagon. So I know I need to find the area of one hexagon, plus there are going to be 6 triangles. Since it is a regular hexagon, we know that all 6 of these triangles will be the same. So if we can find the area of one triangle, we can find all 6 of them. Now, how are we going to find all this? For the area of the regular hexagon, we're going to be using the formula 1/2 the apothem times the perimeter, which is what we learned in our previous units. The perimeter of this regular hexagon, since one side is 10, the perimeter of this hexagon is going to be 60. The big thing we need to find at this point is the apothem of this hexagon. So if we come back to our picture, remember to find the apothem, draw in one of those triangles from the center of the hexagon. We're going to divide that triangle in half. This is the apothem that I'm going to be looking for right here. Since this was a hexagon, we know that this was in here, this was a 30, 60, 90 triangle. And when we split this 10 in half, 5 and 5, that's going to allow me to find the apothem here as 5 square root 3. And again, all I'm using is that 30, 60, 90 that we learned about several times now, okay? So now we've got this apothem, 5 square root 3. And all of that gives us the area of this one hexagon. As for the triangles, to find the area of a triangle, we have to do, I'm going to switch colors here. To find the area of a triangle, we have to do 1/2 base times height. So let's think about one of these triangles here. Okay, I'm going to kind of color this one in a little bit. What information have they told us in the problem? We know that the edge of the base was 10. We already kind of included that down here at the bottom. Now that also means that over here, this is 10 as well. The other thing that we're told is that the height of the pyramid is 15. Now I want you to notice that I did not call it slant height. Okay, this is just the height of the pyramid. This is not the slant height. And that does make a big difference here. So when I come back to my diagram, the 15 meters is actually this height right here, 15 meters. Now, how could we use that to help us figure out the slant height? Because that's what we're missing right now. And we're gonna need that slant height to be able to find the area of one of those triangles. Okay, so if you think about the triangle on the inside here, okay, we have this height of 15. Actually, let me change the color here to red. We have this height here of 15. We know that the distance from the center point directly to the middle of the edge, remember guys, that's just the apothem. It doesn't matter where it's drawn, it's just the apothem. And we already know that that apothem is 5 root 3. So if I redraw this triangle off to the side here, I know that this is 15, I know that this is 5 root 3, and what I'm trying to find, go back to my pyramid, what I'm trying to find is this. So what I'm trying to find here is this side of the triangle. This is going to be my slant height. And since I know 2 of the sides of this right triangle, I can plug these into the Pythagorean theorem to find that the slant height, this is going to be 225 plus 75, that's 300. And I'm going to actually leave this in simplest radical form. If I take the square root on both sides, I can split this up into the square root of 100 and the square root of 3. So my slant height is actually 10 root 3. Okay, now keep in mind that that slant height is actually the height of one of the triangle lateral triangles. So now I can go back up to my formula for one triangle, 1/2, the base is 10, that height or slant height was 10 root 3. And since we know that there are 6 triangles and they're all the same, I'm going to multiply all that by 6. Okay, so lots going on here. Let's do a little bit of simplifying. Okay, starting over on this end, I know that half of 60 is 30, and 30 times 5 is 150. So my one hexagon is 150 root 3 plus, okay, over here on the other side, 1/2 of 10 is 5. 5 times 10 is 50. 50 times 6 is 300 root 3. And since both of these have a root 3, I can add these together for a total surface area of 450 root 3. And surface area is in squared units. So my final answer here is 450 root 3 meters squared. These problems do get a little bit complicated, which is why I wanted you to see maybe one more example where we're kind of breaking it down. What's really key is that you're understanding some of the key parts of the pyramid, the difference between slant height and height. the fact that, and maybe I'll make a note of this down here, the fact that your slant height is the height of one triangle. Actually, let's call it a lateral triangle. Okay, so when you find that slant height, you're actually finding the height of one of those triangles so that you can then find the area of the triangle. So some things to think about and some things for you guys to try in your homework tonight. I'd like you guys to try finding some surface area of some different pyramids. Remember, you can use formulas. If it is a certain type of pyramid, like a tetrahedron, you could use our formula for surface area, but make sure you show what formula you use and what numbers you're plugging in. If it's any other right pyramid, you could use these formulas. Which means you will still have to know how to find the the slant height. Or you could go back up to method 1, and rather than working on a new formula, you could just break it up into individual pieces and find the area of each individually.